In this video, we will be discussing how nerve impulses are transmitted along neurons. A resting neuron, which is one that is not transmitting an impulse, has potential energy. And this potential energy is in the form of an electrical charge difference across its plasma membrane. And this is called the membrane potential. The setup is that the cytoplasm just inside the membrane is negative compared to the fluid outside the membrane, which is positive. The electrical potential, or voltage, across the plasma membrane of a cell that is not conducting an impulse, or is at rest, is about negative 70 millivolts, and this is called the resting potential. So how is this resting potential established? It exists because of differences in the concentrations of ions inside and outside the cell. And it is set up by the sodium-potassium pump. The sodium-potassium pump is maintaining gradients of sodium and potassium ions by using energy from ATP to move 3 sodium ions out of the cell and move 2 potassium ions into the cell. As a result, there are more positive charges outside of the cell, and that gives the outside its positive charge compared to the inside. So a nerve impulse is created by an action potential. And an action potential is the reversal and then restoration of the electrical potential across the plasma membrane of the cell as the electrical impulse passes along. The first stage of an action potential is called depolarization. So a stimulus, which may come from a sensory receptor, may come from another neuron. There's some kind of stimulus that causes the membrane potential to become a little bit more positive inside the cell. Once it becomes enough more positive, so this is a threshold depolarization, and it's negative 55 millivolts. So once it reaches that, the sodium channels open. So we say that this is an all or nothing principle. If it gets to minus 55, the action potential fires. If it doesn't, nothing happens. And these sodium channels are gated by voltage. So they open when a certain voltage is reached. When the sodium channels open, the sodium ions are going to flow into the cell down their concentration gradient, which will cause further depolarization. So we're creating a positive feedback loop where there's more depolarization, so more sodium channels open. So let's take a look at what's happening here. So you get some sort of stimulus that makes the inside of the cell, so we're starting on the left side of this diagram, makes the inside a little bit more positive. So if it reaches threshold, then these sodium channels are going to open and sodium is going to flow into the cell. And that's going to occur and it's going to reverse the polarity, right? So now you see that in that region, the outside of the cell is negative and the inside of the cell is positive. And that's what's called a depolarization. So continuing on, the next stage is repolarization. So there's been this switch in membrane potential. So now the sodium channels are going to close and potassium channels are going to open. And the potassium ions are now going to flow out of the cell down their concentration gradient. So they're flowing opposite to the direction that the sodium flowed. So this flow of potassium ions out of the cell returns the membrane potential back to its resting levels. So let's look at what's happening there. So here on the left side of the diagram, that region of the membrane has been depolarized. Okay, the potassium channels are now going to open. Potassium is going to flow out of the cell. And this is going to put the positive charges back outside so that the membrane potential can go back the way it was. However, this is not what the neuron looks like in its resting state. Right? We've got the potassiums and the sodiums are on the wrong side, on the left side. So at this time, we get what's called a refractory period. So there can't be any action potentials in that region of the neuron because the sodium and the potassium aren't in the right spots. So what happens now is that sodium-potassium pump goes to work again to restore the original concentrations of sodium and potassium. So this is a graph that shows what's happening to the voltage as an action potential goes through a region of a nerve cell membrane. So you start out at resting potential, negative 70 millivolts. If threshold is reached, it will depolarize. But there may be some failed initiations. So there's a bit of a stimulus, but it's not enough to reach threshold. So there is no action potential. Okay, and this is the all or nothing response that neurons have. If the stimulus is enough to reach threshold, we get this large depolarization of the membrane, followed by the repolarization, entering into the refractory period where we're setting all the ions back where they came from, and then return to rest and ready for another action potential if it comes along. So how does an action potential move down a neuron? So we've talked about how an action potential exists in a certain location. How does it move? So here we're at the point during repolarization where the potassium ions are going to move out through their channel. The sodium ions are going to move within the cell, and that's what's going to cause the action potential to move. Okay, so the action potential in one part can cause an action potential in the next section, and so on and so on and so on. And this is because those sodium ions are moving within the axon. So as the potassium's moving out and the region of the membrane is repolarizing, that sodium is diffusing down the cell where there are less sodiums. And as it does that, it causes that initial stimulus, that bit of positive charge, that can then open sodium channels. And now sodium rushes in this area, and we get a depolarization moving down the axon. So now the depolarization has moved further along the neuron. And then that just continues. Those sodium ions will diffuse further down the membrane, causing an action potential in the next region. So one last idea is that of myelinated neurons. So a lot of axons are coated with what's called a myelin sheath. And this myelin sheath is made of specialized phospholipid bilayer that's produced by Schwann cells. And Schwann cells are a type of support cell, those glial cells that exist in the nervous system. The myelin sheath's job is to insulate the nerve by preventing the loss of ions. And the myelin sheath is in sections, and the areas between those sections are called the nodes of Ranvier. So what happens is the nerve impulses that we've been talking about can jump from one node to the next, and this increases the speed of nerve impulse transmission.